Hi, Jakub here. Welcome to my presentation about profiling your PowerShell code with Profiler. Before we start, let me show you the sponsors of this event. And also, let me say thank you to all of those sponsors because those are the ones who enable this conference to happen. And also thanks to all the organizers who are spending their time organizing this event. It's really a pleasure to be able to speak here. Now let's jump right in. So before I will show you the innards and details about Profiler, let me just show you a quick overview of it. So what you can see here is an output that you would get from Profiler, and it only has 3 commandlets, so it's really simple to use, and it's also really simple to install, as you will see in a second. And what you see here is the output of the module. On the top, you can see that we're calling this command called trace script, which is what Profiler provides. And then you can provide it a script block. And we take a script block not because we don't support running files or scripts or modules, but because a script block is the easiest way to provide code to a module. So you can provide your file, you can provide a call to a module function, you can provide just a piece of PowerShell script, and all of that can be provided using a script block. And it will also run in the correct context, so it will run directly in your script. So if you define any variables beforehand, those would be available inside of the script block. So it solves a lot of headaches for us and for you. Everything is just super simple. Underneath that, you can see that we are running in PowerShell 7, and it's starting the trace. And then there is this glyph, and that's where all the output of the script that runs underneath would normally be. In this case, you might notice that I'm running pester test. So this is a script that runs all of my tests inside of pester. Even though this is not a talk about pester, I'm still using pester for some of the examples, and because it's a big payload and it's very complex module, so I'm using it to make sure that Profiler would work for your workbase as well, because your script might be maybe way more complex than mine, or maybe way more simpler, but pester is still a significant workload for Profiler, so it's really nice to know that Profiler can work with it. So this is where all the output would be, and then we are done tracing, and we collected almost 3 million events. And then we have to post-process them to make some sense of them and see what is slow and so on. And this, you can see, takes like 2 seconds, which is also nice because when I started developing it, it took maybe like 2 minutes to post-process 2 million events. So I had to use a combination of Profiler and other profiling tools to make sure that this is faster as well, which was also a pretty nice check for me to ensure that I'm delivering a performant module. Underneath that, in the yellow typing, we can see that it took 1 minute and 8 seconds to run, and then it tells me exactly what I need to run to get the results. It even mentions the exact variable that I specified up here, which is a little neat trick that you might look up in the codebase if you're interested and pick it up for yourself as well. Now, I do that. I ask for top 50 self-duration, and I format table, and all of those properties I name here, you don't have to name them. It's just me doing that so you could see it on the screen and it fit nicely. There are few yellow dots that I added in post-processing to show which lines I consider to be slow, and you can see that almost all of them are related to testdrive.ps1. If you know pester, you know that test drive is like a small feature inside of pester that allows you to have your playground, like an empty folder where you can put your files and it will clean them up automatically. It's really a small feature, and we can see in the profiler that it takes almost 20 seconds of the whole run, which is a very significant portion because the whole run was 1 minute and 8 seconds, and we have test drive, which is a small feature, taking 20 seconds out of that time. So there is something broken about the performance of test drive, and I should definitely go and revisit it. Profiling pester code took me like 5 minutes, and then I spent maybe 50 minutes fixing the problems. And those are the results that I've got after spending 1 hour with Profiler. This is running on a different code base, so the numbers that you see are different, but what's important here is the difference between the numbers before in version 5.2.1 and in version 5.3.0 Alpha 4. That's after the performance fixes. So on a smaller test base, I was running 18 seconds in the previous version, and then after spending 1 hour with Profiler trying to improve the performance, it's running in 8 seconds. So that's 10 seconds less, it's 2 times faster. And if we run it on a second run, which sometimes happens when you run tests locally, but not usually on CI, it is even more significant. So once the PowerShell session warms up, you can see that we run for 12 seconds in the old version, but for only 2.5 seconds in the optimized version, which is an awesome improvement. But it's not just me having some fun using Profiler. Take, for example, Guido here, who used PS Profiler to identify some heat spots in scripts that was at his customer site, and he aced it, and he reduced the runtime from 11 minutes to 1 minute, which is pretty significant improvement, and it's something that can like go into your resume, or you can ask for a big bonus at the end of the year. So don't wait. Learn how to use Profiler. It's a skill that you might use today or tomorrow or maybe even in a month, but it's still a useful skill to have. So let's go and install Profiler on your system right now. Just go to a PowerShell command, PowerShell terminal, and do install-module Profiler, and it will just automatically install it for you. There are no external dependencies that you would have to set up. It just is a normal module that can plug into your PowerShell session and it can profile your code. If you're having any problems with the module, go to my GitHub repo, which is at github.com/nohvnd/profiler, and report an issue there, and I will try to help you. So if you're not doing it already, go into your console now and do install-module profiler. So now, when you're hopefully installing the module, let me tell you what the agenda is. So there are some performance considerations that we have. Then there will be profiling your code, how to actually do it with Profiler. We will use the trace-script commandlet. We will use flags, which is a feature of both trace-script and invoke-script. And we will use the invoke-script commandlet. Then we will talk about few patterns, how you can optimize your code. And then I will show you the new pester code coverage, and I will probably also show you how Profiler looks inside. If there are any questions, please go ahead and ask them in the chat, because this is a pre-recorded session, but I'm still in the chat waiting for your questions to be able to answer them. So if there is anything on your mind that you want to ask, just go ahead and ask me, please. So first, some context. Let me tell you about my naive approach to PowerShell performance before I started with Profiler, before I created a tool, and before I had any way of measuring my PowerShell code performance. So what I basically did was stare at the code, guess how many times it is executed, and hope that my changes will make it faster. So I did this when I was optimizing Pester 4 and Pester 5, and I did it for maybe a month. Like between the version 5 beta and 5.0, I really wanted to improve the performance. And so I spent a lot of time just staring at the code, trying to find some places where it could be slow. And when I found those places, I created a small prototype, and I tried to invoke it 1 time, 10 times, 100 times, and see how much time that took. And then I tried to kind of guess, is this, how many times would this actually be in the real life invoked? If I'm invoking something 1,000,000 times, it's pretty sure that it will take a lot of time. But if the end product, in this case, the pester module, will just invoke it once, then I'm not saving any time, I'm not measuring anything real. And then when I found in the code that it's invoked multiple times, I looked at what changes I can have to make stuff faster. And I went into code, did the changes, and I didn't really have any good way of measuring how much progress I'm doing and so on. So with that, let me show you an example of how that looked like. So this is my code. This resembles roughly something that is inside of Pester module, and that is filtering of tests. What happens inside of Pester is that I find which tests you have in your files, and I look at what names and tags they have. And if you want to filter down to just tests with a given tag, I have to go through all of those tests and reject those that don't have the correct tag. So in this case, we're looking for all the tests that have the tag Windows. And I have a collection of them. There is 5,000 items, but only 2 of them have the correct tag. Only 2 of them have the tag Windows. So to filter those tests, I use something like this, a function called filter test. And then I pass the test, I pass the tag, and if the tag is the expected tag on the test, I just return the test. So this filters down the tests. It's pretty much like using where object on the whole collection. Below this, I'm just measuring the time, checking the tag Windows, and I just have a for each loop in which I take every single test, pass it inside of the function, and that will return directly into this filtered test. So if I run it now, you can see that it takes 110 milliseconds. We can run it one more time to see that this wasn't a fluke. It's usually around 100 milliseconds on the system. Is that too much? I don't know. Like it can be okay. It's 5,000 tests, 5,000 objects. Maybe this is fast enough. But maybe it's not. So if I did this in 10 places in the module, it would take 1 second, and that's already a noticeable delay. So let's try to see how we can optimize this. I have the same code here. Again, 5,000 test objects with 2 of them with a tag Windows. And now I changed the code a little bit. Instead of calling the filter test function every time inside of a for each loop, I pass the whole array inside of the function and then just call the for each loop inside of that function. So instead of calling the function 5,000 times, I will call it once, and then I will use this for each and if, which are pretty basic statements inside of PowerShell, and they are pretty fast. I just use that to filter those tests. So let's run it one more time. Or let's run this new fixed version for the first time. It takes 5 milliseconds. And if I run it one more time, it takes 2 milliseconds. So now we optimize the code from taking 100 milliseconds to take 5 milliseconds, which is pretty awesome improvement. Or is it? If this would run only once inside of my module, then we saved how much? 95 milliseconds. That's almost non-noticeable. But maybe if this happened 10 times in a row, or the problem was there 10 times, we would be reducing 1 second once we would fix the problem in all of those functions. So that would already be a pretty noticeable improvement. For me, this was worth it, so I made this change inside of my module and used it. But this kind of boils down to 3 questions. Which code is the slow code? Oh, let me switch back to the slides. Which code is the slow code? Which code is worth optimizing? And how do I optimize it? Those look like problems with the same difficulty, but actually the last one is the easiest one to solve. Because if you have a little piece of code that you know that needs optimization, you can just grab it and you can just share it on a forum, and people will jump at it and they will try to help you. But if you take your whole script that has like 10,000 lines, No one is going to read through all of that, analyze it, try to fix the problem, and find the exact 2 lines that needs to be changed. Unless you pay them, of course. So how do I optimize it is not really that much of a problem, because there are forums, you can ask people, you can come up with it yourself. There are pretty basic stuff. The bigger problem is which code is slow and which code is worth optimizing. And that's where Profiler can help you identify those pieces of code. Again, if there are any questions, please ask them in the chat. So let's start with the first one. Which code is slow? Okay, let me jump to the example first, and then we can go back to the small pieces of code. So which code is the slow code? I have a pretty similar example to the one as before, but I expanded it a tiny bit. Now, instead of just having a single tag on a test, you can have an array of tags. And we are trying to look for a test that has at least one of those tags that we specify. So I have 5,000 tests again. I have this function, which in my real module kind of naturally emerged. So it's pretty difficult to figure out if there are any items in an array and make the function still compatible across all the versions of PowerShell. And because I needed to support PowerShell 3 and up, I decided that I will just hide this logic inside of a function once I figure out how exactly to do it. So I came up with this: if the array is not null, and there are any items in the array, then the array has some items. So that's the function that I call any. And then once I have this function, it's pretty easy for me to reuse and define, for example, a none function. And so a none function is just an inversion of the any function. And then when I have none, I can go to my filter test and say, if there are no tags, then this must not be the test. So if it has no tags, it doesn't have the tag that we are looking for. And so I just return. And then there would be more logic in this function that would look at the tests that actually have the tag. So this is not a really good optimized code, but this is how it kind of emerged in my Pester module. And I didn't know this is slowing me down in many places. So that's what I'm trying to look at with Profiler. And then I'm just filtering those tests again inside of a loop. And you can notice that there are extra curly braces because all of this is hidden inside of a script block. So all of this code I will be profiling. I've put it in a script block, and then I give it to this trace script commandlet. The trace script commandlet is coming from the profiler module, and I provide the script block, and I will be receiving a trace. So let me run that. And oh no, it tells me that I don't have this function imported. That's because I have automatic module imports disabled for unrelated reason. So let me just do import module profiler, get module profiler, so I can show you that it's imported, and it really just exports those 4 functions. So we are right now invoking this trace script. Running that, you can see the familiar colorful output, and this is the actual output of my script that's being measured. This time we received only 75,000 items, so not 3 million. And it took 779 milliseconds to run this. And then it tells me again, run trace top 50 duration and pipe it into format table. So I'm doing that on this line here, but I'm also listing all of those properties that I want to have available on the screen, because there are many more and I don't want to pollute the screen too much. So I'll just make this a tiny bit bigger. And what you can see here is that first we have this percent tab, percent column, which says how much time of the overall runtime this line took and all the code underneath it. So all the code that the filter test did call is put together, and that took 647 milliseconds, and that's 83% of the overall time. If you started adding up those numbers, they don't add up to 100. They're just really saying that 647 is 83% of 779. We can see the location, we can see where, on which line exactly it is. So it's in which code is slow, line 38, and it says that this line is slow. It also tells us that this line is slowing us down and this line is slowing us down. So all the lines that contain our functions are slowing us down in some way. And because there's really nothing else happening on that line, we can guess that the slowdown is actually the function call. Because as I shown before, in some situations, just calling the function can be pretty slow and slow down your script. So now let's see how to fix that. So again, I have 5,000 test objects, and I moved the loop inside of this function as we did before, and I also expanded the none and the any call into this code, which is just raw PowerShell, which checks the size of the collection and returns if there are no items in that collection. So now if we run the code, we can see that instead of taking 703 milliseconds, it took 602 milliseconds, which is way less than before, and we optimized it to be just much faster. And most of the time is actually coming from us generating those items because we are still doing that inside of the script block. So using Profiler helped me identify the hotspots in my script. I was able to eradicate them and optimize the code to be much faster. In this case, I'm optimizing something that is not really that often being optimized inside of your script, and it's probably not going to be that often optimized in your script, because the function calls, even though they pop up as pretty slow in this example, are usually your least concern in your real scripts. You really have to look at the output and look at those first items on the list and identify what is actually slowing your script down, because those are just like canned examples that I can fit on the screen, but they don't exactly represent what will happen inside of your code. And also my concerns in my module Pester are a bit different than what you might have in your own module, because I needed raw performance and I didn't really care that much about the code being nice inside, and I can, I don't know, in some ways handle it because I have covered it in many tests. But for you, this might not be the preference. You might not want to sacrifice the niceness of the none function to replace it with the ugliness of this null equal stack and so on. So those are some of the considerations that you have to think about, and think about what is the actual thing that I'm looking for, and how much further I want to optimize this. Is this performance good enough for me already? So TraceScript is really useful function, and you can use it to profile a lot of stuff. If you're just looking to start profiling something, then what you can do is that you profile a script, any script that you have, and pass in parameters. Just create a script block, use the ampersand, and then provide some parameters, and it will trace the script. What you can also do is that you profile a module, and you can profile it including the module load. So for example, if your module typically just runs once, maybe it runs inside of a CI pipeline and you want the performance to be fast, including the load of the module, this is how you can profile it. Or maybe your function is called multiple times and the import module is just called once, so you would just take this line and you would exclude it from the script block. You would move it up here, and then it would just profile the getPlanet function. So those are different approaches that you can use. Or you can use your profile that you have inside of your PowerShell command, PowerShell console, and you can profile it. So you would start a PowerShell session with no profile, so it doesn't load it, and with no exit, so you can poke at the data. And then you would say trace script dot source the profile script inside of my current session, and that would profile your startup script, and you could use it to like make faster experience when you click the new terminal in your Windows terminal, or however you are starting your new PowerShell session. Or you can just profile just any script block. Like as in my demos, I just take a piece of code, put it inside of a script block, and then provide it to trace script, and then just run it, and then I see the output. So any questions so far, please post them in the chat. I will be waiting for them in there. So we already went through the example number 2, actually. It's the trace script one. Now we can look at duration and self-duration. Those can be a little bit confusing, and you can see them here in the output. Let me just switch back to the scene. So here we have a duration, and here we have a self-duration. And you can see that for this, those are pretty different. So this one is like 8 milliseconds, and this one is like 1/10, 100th of a millisecond. I'm not sure. So what those signify are how much time was taken either including all the code that run inside of the call or on the line itself. Here's a better example. So we have this function f, which just calls start sleep inside of it, and then we trace it. And so here are the two outputs. We first order by top 50 duration, and you can see that the function f pops up on the top. The duration is how much time we've spent calling the function f and invoking all the code inside of function f before returning it. So how much time we spent from calling the function till returning from the function. So this includes all the code that runs inside of the f function, and it includes the start sleep that's inside of it. So once we enter the function from here to here, that's what we measure as duration. And then we have self duration, and that measures only how much time was spent entering the function. So this is not included at all. So we just include how much time we spent entering and leaving the function, but not the code that was running inside of it. So in this output here, you can see that f took not even 1 millisecond, it took 1 second of duration because it includes the start sleep in it. But if we look at the self duration, it didn't take not even 1 millisecond because entering and leaving the function is relatively fast. And if we then look at self duration, we can see the lines sorted by what actually took the most time, like the small pieces. And in this case, start sleep, it doesn't invoke any code that is visible to Profiler inside of it, because this just calls to the .NET. So you enter this function, stuff happens, it is happening for 1 second, and then it leaves the function, and that takes 1 second. So that's why it has self duration of 1 second. And because the duration is the same, because we enter this function and leave this function, and all of this stuff that's happening inside of the function also takes 1 second, then duration for start sleep is also 1 second. So to sum up, Self duration shows you the small pieces that are actually slow in your script. Duration, on the other hand, shows you the bigger pieces that contain the smaller pieces that are slow. So if you have a function that calls start sleep or something else that takes time like 100 times, you will see that this function would be itself slow. But then if you look at the small pieces, then the innards of that function wouldn't really show up because those would be there 100 times. So if you're looking for stuff to profile, definitely always start with cell duration. If some stuff is on the top of the list, you can go ahead and you can optimize it. Once you will run out of those pieces and they stop making sense anymore, then look at the output ordered by duration and try find like which areas of the code take the most of the time. So this is just a summary of what I just said. Start with top 50 self duration to see which code is the slowest. And then once you run out of options in that view, just look at the top 50 duration to see which parts of your script take the most time. And you have to decide for yourself if that's appropriate because you know your code, you know which pieces should take a lot of time, and you know the pieces that definitely shouldn't take a lot of time. But if they do, definitely look into them. Now let's ask the question, which code is worth optimizing? And that's the golden question, and Profiler can help you identify the places where you can start with your optimizations. So I've shown you this screenshot before, and you can see that I could see here that the test drive is really taking a lot of time from the execution, and that's something that I definitely know shouldn't be this slow. So I started looking at it, but then, for example, you can look here and you can see that we're taking a lot of time writing the pester debug messages. And that's something that I know is not really happening in my production build. And I also am testing the output of the debug messages in many places. And those take a lot of time, but this isn't really happening in the real world scenarios. So this is just an artifact of running the profiling over my tests, because in my tests, I'm invoking write pester debug message many times, and I'm reporting debugging even in the cases where I'm not normally doing it in the production code. So I know that this is totally not worth looking into and optimizing. So Profiler can only tell you which code seems slow. It can only tell you like how many times it is invoked, how much time it took by itself, how much time it took overall, but the deciding of what actually has to be optimized is up to you. I usually just start by looking at all the lines that are in the top 10 and try to figure out if those are worth to optimize and if there's anything I see at the line that I can do about this code. So maybe like look at this, like invoke script block. I don't know how I would optimize it. Maybe make the script block smaller, but which script block is invoked there? It's the script block that the person provided. So if they provided a big script block, it's going to take time. If they provided a smaller script block, it's going to take less time. I cannot really optimize that without like removing their code that they provided. So there is nothing I can do about this. On the other hand, in this get test drive, I know that I can maybe replace this with a call to a .NET method, which might be faster. So I will go and try that. Or in here, I'm getting PS drive and then looking at the root. And I know that I can just do that once and save the value and reuse it instead of every time querying get PS drive, which appears to be pretty slow. So those are the kind of ways of thinking that I have when I see this output. And you have to apply this for your own code because you know what is happening inside of your own module. So start by looking at percent and hit count. look for code that runs many times for every item that you have if you're processing items. And then when you can optimize that, then you optimize it for every single item. And that's one of the advices that I can give. So now that you've found some code that you want to optimize, let's look at how do you actually optimize it. So there are multiple techniques that you can apply, and I'm just going to show you one, which is looking at the biggest performance killer that you are about to encounter in your PowerShell scripts, and that's using plus equals to add items into collections when there are many items added into the collection. So I'm running this. It's taking 10,000 items and adding them into this empty array. And what happens here when you use plus equals is that every time you add a new item, sorry, let me switch to the code. So what's happening here is that inside of a for each loop, I'm adding an item into the array on every iteration. And what happens every time you add a new item, it will take the array, have to copy it into a new bigger array and add the single item. And this happens on every iteration. This is really slow way of adding items or outputting items into an array. And you can see it in the output. It takes 2 seconds to complete this. And you can also see in the profiler output that this code is really slow. So it's the plus equals that takes most of the time executing. So let's try to optimize it. And what we do is that we just output in the array directly from the for each. There is no adding into the array. There is nothing slowing us down. We can run it and it takes, well, it's done almost immediately. So it takes almost no time at all. So we did this optimization and it's pretty sweet. And you can see that it takes like 2 seconds less. But what does it mean for a script? It will be faster, but how do I know I did a good job optimizing this? Well, here you can see it directly because it's just way faster. But what if you are in a real life code where the change is a little bit more subtle? So that's where flags enter. And flags are a feature of Profiler where you can wrap your code inside of an if statement, and we will define a global variable that will be used to switch between the different pieces of your code. So you can see here that this is the older example, the slower one, and this is my code that is optimized. And I'm using this magical variable called profiler_array. And if you notice, that's what I define in here. So this should be true. And let's just remove this for now. And then if I run it, you can see that now it's fast. And if I change this to before, it will be slow. And if I remove this, it will be fast again. So what's happening here is that to trace script, which is the commandlet exported from Profiler, I provide this -flag parameter and give it a hash table. The hash table contains keys which have values, usually Boolean values. That's what I would recommend to use. And each of the names in the array, in the hash table, is then defined as a global variable that you can use inside of your script to switch between different paths through your code. And the niceness of ifs inside of PowerShell is that you can wrap them around functions, and you can wrap them around the whole body of a function and so on. So you can use this to switch between the old implementation and the new implementation. And I usually use this when I'm like looking into a bigger problem, and I try to see like, this is how it ran before, this is how it will run once I'm done optimizing it. And this is a hash table, and this represents the site that's after. So if this is set to true, this variable will be set to true when we specify the -after, or when we don't specify anything. And you can also see that in here in the output, you can see this A and B. Those tell you if this was run with the after setting or the before setting. This is all nice and dandy. You can just like switch it manually like that. But what if you wanted to do measuring a bit more, I don't know, automated? And that's why there is also invoke script. So invoke script is another commandlet of Profiler, and you can use the same functionality, flags, to switch between the previous and the new state. And you can tell it how many times you want to repeat that, if you want to have any preheating, so it will run like one time before it will start measuring. This is good for checking startup performance or non-startup performance and so on. And so what we do here is that we will end up just switching between those two code paths automatically. So let's see what happens. We run before, after, before, after, before, after, and now we're done measuring. And you can see that the before was usually 2 seconds, and then the after was, well, very, very small number. So we can see that we are continuously better performing in the after state, and so this is a good performance optimization. So this is how you know you optimized it well, that before it was slow and after it's fast. That's how you know you did a good job optimizing it. Now let me also tell you about Pester code coverage. And you might ask, how are those two connected? But this whole project started as an attempt to bring faster code coverage to Pester. It ended up being a profiling tool, and then I took parts of the profiling tool and reused them for the code coverage tool inside of Pester. And they kind of interoperate together, so you can enable code coverage for your code, and you can also measure performance of that using the profiler. I enabled that because, well, I just wanted to do it. And so profiling and code coverage are pretty different on the outside, but internally they are pretty much the same or pretty similar. So profiling asks about all the code that run. It asks which code has run, but it doesn't really care about the code that didn't run. Then it asks how many times this piece of code has run and how fast it did run. Code coverage is pretty similar, and it doesn't look at all the code, but only at the code that you want to inspect the code coverage at, usually your whole code base except for the tests. But you don't want to inspect modules that you're calling and so on. And then it asks which code has run, and it also asks which code didn't run. So that's different from the profiling. And it doesn't ask, did this code run multiple times? It's okay if it runs just a single time, because then we can consider it covered, and it doesn't care about how fast the code ran. So in Pester, we have this old code coverage that is using breakpoints, and breakpoints are really not suited for this job, because once you will start adding more than 100 breakpoints into PowerShell session, it will start being really slow for all the execution. And we are sometimes adding thousands or tens of thousands of breakpoints when we're doing this. So we're kind of misusing the tool that was never designed for doing this. And so the performance is getting worse and worse. And if you have a code base that has like some code, like one size, it for me took 13 seconds. But then when I took the code and copied it 4 more times just to have it instrumented with the breakpoints, the execution now took 99 seconds. And then if I doubled that, it didn't double the time, it tripled the time. And so it's really, really bad for performance to have more breakpoints. Compared to that, using the new profiler-based code coverage, if I do this in Pester, it will take half of the time of the previous run in the first place. But then if I double the size, or if I make the size 5 times bigger, it will still take almost the same time. If I take the size of the code and make it 10 times bigger, it will take 12 seconds. So it doesn't grow as much, it doesn't grow that rapidly as the previous one. And it's just way, way faster than it was before. Here are some numbers if you want to dig into that more deeply, but definitely what I can recommend is that if you're testing with Pester now, go and enable the new code coverage. It's available in Pester 5.3, and you just do it by using the configuration, code coverage, use breakpoints, and set them to false. If you want more details, just go to the Pester repo, or you can start discussion there, or you can look at the link that's linked inside of the slide. But definitely check it out, because code coverage now became much, much faster, and it's pretty much a shame not enabling it for every test project that you have. So now finally, a summary, end of this talk. Let me just tell you one thing. Just do try this at home. Just install it. Use Profiler, profile some scripts, some that you got at work, some that's your toy project, some that you're working with every day, and see what's slow there. See if there's something that you can optimize, see if it breaks Profiler totally, and then report it on the GitHub issue. Just get involved in some way, because this is a very, very useful skill to have, and hopefully it will help you improve your performance, and hopefully it will help you get some good feedback, and you can brag in front of your friends about your